then we put these numbers in ascending order, right? Smallest to largest. So we have a sliding window of things we compare. So first we're gonna look at these two numbers, 17 and 3. And if they're out of order, we're gonna swap. So in this case, they are out of order. So number 3, 17, 61, 0. Right? And then regardless of whether or not we swapped anything, we move our window over. Okay, so then we compare the second and third numbers, which in this case is 17 and 61. Those are already in the correct order. So we move our window over again. 61 and 0, compare those, they're not in the correct order, so the resulting array is 3, 17, 0, and 61. Okay, that's our first pass. So all of that occurred when I was equal to 0. Okay? So now we're at the bottom of the loop. We come back up, increment I to 2, or excuse me, to 1, which is still less than n minus 1. And we start over with k. Except now, instead of k going up until it breaks the test that's n minus 1 minus 0, which is n minus 1, now it's going to be n minus 1 minus 1, which is n minus 2. Okay? And why is that? Because the way bubble sort works, remember I used the example in class the other day, I said, when I get a hand of cards, I get my hand, I look at the leftmost card, say, oh, that's an 8, I compare it to the stuff next to it, let it bubble up, I take the new first card, move that over as necessary, so things are bubbling to the top. But the way bubble sort works is that we're guaranteed that on the first iteration of the I loop, right, the first full pass across the numbers, that at the end of that, the largest number, no matter where it's at in this set, will be in the last position. Okay? And then we're guaranteed that on the second pass, regardless of where the second largest number is, it will be in the second highest position, and so forth. So there's no reason to keep moving all the way across the numbers, because we know that 61 is never going to move from the end. Okay? So what this inner loop does here, the 1k, is it slowly starts to shrink the range of numbers that we look at. Because we already know the stuff at the end is never going to move. After the first pass, the largest numbers at the end. After the second pass, the 2 largest numbers are at the end. Third pass, the 3 largest numbers are at the end, and so forth. Okay? So, next pass. So at this point, when we start I is equal to 1, here's the array as it stands. 3, 17, 0, and 61. Right? So now we compare 3 and 17 again. Those are fine. I compare 17 to 0. Those are out of order. So I get 3, 0, 17, 61. And going back to what I said about the K loop here, there's no reason to compare 17 to 61, because I know 61 is not going to move. All right? So here's the current state. All right? So I did 3 comparisons on the first iteration, 2 comparisons on the second iteration. Start again, I'll compare 3 to 0. Those are out of order, so I get 0, 3, 17, 61. And because of this, the range for K, that's the only comparison I would make on this.
Can you show me where in the code it stops you from comparing the 17 and 61?
It says while K is less than n minus 1 minus I.
Oh, so it's in track.
Right, so as I goes up, this right-hand side goes down. Okay? Everybody open on that. Okay. I'm trying to see how he's going to answer this. He's trying. Right. So this is the final array. And so we perform 6 comparisons. Okay? Any questions about that? Okay. So let's analyze this. So if we're thinking ahead, and actually it'd make more sense from the second version, but if we're thinking about the best case scenario, without knowing anything else about the algorithm, I would think best case means the data's already sorted, right? 1, 2, 3, 4, right? So data already ascending order. The issue here, though, in terms of what does it mean to say best or worst or average, is this outer loop always runs n minus 1 times. right? There's nothing in the logic here that says, oh, well, if the data is already sorted, don't keep going. The I loop always runs n minus 1 times. And the K loop is essentially fixed. Now this boundary here changes, but the range of values that the right-hand side of this inequality goes through is the same no matter what the data looks like, right? Once again, it doesn't do anything to say, is the data already sorted, so there's no reason to keep looking at things, right? So what do we ultimately get there? So let's build a table. And I was talking to somebody earlier about homework. For me at least, for lots of things we do, it helps to build a table, right? It allows me to easily see the costs. It allows me to easily see patterns that we're gonna need to find in order to find closed form solutions. And also, in some cases, just gives me something to go back and verify. Because if I get to a point and I say, oh, well, the formula for this is, 3n minus 20, well, then I can go back through it and say, okay, what was my n here? Did I really get 3n minus 20, right? So I'm looking at this and trying to figure out how things work. So here I have, so I go 0, 1, 2, at n minus 2. Technically it's n minus 1, but we're only talking about the part that's relevant to the inner loop executing. Okay, not the part that stops things, all right? So the last value of I that will be used on the inner loop is n minus 2, right? Because once it reaches n minus 1, it stops. So what's our formula? N minus 1 minus I. So that's n minus 1 minus 0, which is n minus 1. And then the next line, let me draw some lines here. N minus 1 minus 1, which is n minus 2. N minus 1 minus 2, which is n minus 3. Dot, dot, dot. And eventually, what we're ending up here with is n minus 1 minus n minus 2, which would be equal to 1. And that's what we saw when we did the example, right? By working through the example, we saw that last time, we only had to make one comparison. All right? So now we need to sum these up. How many internal loop iterations? Because this is what we're counting here. So in this case, I guess you'll say what we're counting. We'll say, how many, let's say swaps. We're just counting the total number of times that this code right here executes. Okay?
For this one or for like the best case?
For this, this algorithm.
Okay.
Let me think ahead. Do we need to do comparisons? They're not necessarily the same. Well, let's change that. We'll claim that's really comparisons. Because they're not technically the same. As we're gonna find out, the reality is because of the way the loops are constructed, we always run the same amount of time. So there really is no distinction between best order. So data that's already sorted versus data that's completely reverse order. There's no distinction for this algorithm between those. It always just runs this number of times. So whatever we come up with is the number of times it's going to ask the question, are these numbers out of order? Okay? So once again, we'll produce this sum here. So our summation equals 0 to n minus 2 of n minus 1 minus I will be equal to n minus 1. It's just summing this column, the rightmost one. Plus n minus 2 plus double dot plus 2 plus 1, which is really 1 plus 2 plus double dot plus n minus 1. Right? All I did was reverse the order. Right? And then we saw, let's do it right here. Right? We already saw before, I'm gonna change the variable, make it more clear. If you have the integers 1 plus 2 plus double dot plus p, the sum of that is p times p plus 1 divided by 2. That's easy to verify. 1 plus 2 plus 3 is 6. So 3 times 4 is 12, divided by 2 is my 6. All right? So I'm template proof, but it's an easy way to make sure you wrote it right. Alright, so what do we have here? 1 up to n minus 1. So the p is the n minus 1. Okay, so it says that's equal to n minus 1 times n minus 1 plus 1 divided by 2. So n minus 1 plus 1, so this becomes n times n minus 1 over 2. Alright? And that's equal to n squared minus n over 2. So we could rewrite this as n squared divided by 2 minus n over 2. And this is our big O, is n squared. And I'm looking at that, but just looking at which of these is the biggest and knowing which one's gonna carry the most weight as n gets bigger. Okay? Questions about that?
So this is the worst case scenario,
Best and
Well,
worst.
that's what you-
both of them.
It's all of them in this case. This is fixed. You pick an n, and I'm telling you the number of comparisons here will be n squared minus n divided by 2. No matter what the data order is. Which is why, for all intents and purposes, best case, worst case, and average case really don't mean much here. It's just what's gonna happen. Okay? But we also, this is big O, so what's the lower bound of this?
It's the same. It's the same.
It's also n squared.
Yeah.
Because I'm telling you, the way those loops are constructed, it's always gonna take n squared minus n divided by 2 comparisons. So the upper bound and the lower bound are this exact same thing. So this is really, so big O is n squared, big omega is n squared. Since those are the same, it means we have big theta is n squared. I said this last week, let me say it again. Best and worst don't mean big O and big theta. Big O is an upper bound on something. That's what it means, it's an upper bound, it's not saying it's best. So you can have big O of the best, you can have big O of the worst, you can have big O of the average. It's just telling you whatever function you come up with can be bounded above by this function.
Yeah, so how do you end up with I as n minus 2 in the table? So again.
Okay,
So we just-
so let's look at how this works again. What value of I breaks this test?
Like what was gonna be?
No, I'm asking you, so if I look at this test here, what value of I will break the test? N minus 1, right? But that breaks the test. So what was the last value of I for which the inner loop, the K loop, ran? The previous one, n minus 2. So I start at 0, and if we're looking at comparisons, this only gets evaluated for values of I to n minus 1, n minus 2, right? Because that last time, then I increments up to n minus 1 breaks the test, but then we don't enter the loop again, so therefore we don't do any more comparisons. Questions on that? Right. Let me see if I can-
Bubble sort always big O of n squared.
This one will be- Let's come back. We may use this one. Alright, so, what's worst case? Well, if I didn't know anything, I'd say, oh, worst case would be the data's in completely reverse order, something like this, 4, 3, 2, 1. But for the way these loops are constructed, where the I loop runs n minus 1 times, and for each iteration, the inner loop runs n minus 1 minus I times, we still get the same exact thing. We still get n squared minus n over 2. Right? There's no variance there, which means big O in the worst case is also n squared. Or technically, you can say it's theta. of n squared. And finally, if we talk about average case, somebody was asking me earlier, said, well, I don't understand what you mean by average case. Let's say I said, well, sometimes my data might be in this order, 4, 3, 2, 1. Sometimes it might be in the order 1, 2, 3, 4. Sometimes it might be 4, 2, 1, 3. All the different permutations of data. How much effort does it take to swap or to compare those, average that out to get the average cost? Well, it turns out it's also, so average is also theta n squared because of the way the loops run. These loops are hard coded, right? If you say n is 10, then the for loop runs 9 times. I can't change that, doesn't matter. I can't put my data in any order that improves that for this algorithm. Everybody get that? So there's still an average. So you look at all the different permutations of those 4 numbers and say, okay, for one of the permutations, how many comparisons did it do? For the second one, how many comparisons did it do? Average all those out, and it still works out to n squared. Because every one of them still takes n squared minus n divided by 2 comparisons. Everybody see that? Let's look at a different version. This is my preferred version, actually. But it can be modified and improved. Let me put the body. So what's here? I'm gonna go right here. I don't really indicate here. Right? Here I'm using a do-while. Some people believe you should never use a do-while because a do-while always executes the body at least once, right? Because the test is at the bottom. But for the approach I'm using here, I want it to execute at least once, okay? And why is that? Because if I have data that's already sorted, I can't know it's already sorted without looking at it once. Okay? So how's this gonna work? So here's the meat of the problem. So So I start off by having this flag variable called sorted. And I set equal to 1 for true. Because I'm making the assumption that the data is already sorted. Okay? If I get to the bottom and sorted is still 1, I say while not sorted, while not true, then that will be 0, right? Which will cause the test to fail and the loop stops. So the point here is to be able to detect at some point that the data is already sorted and quit going back through it every single time like we did before. Okay? So my I loop here is gonna run n minus 1 times. And on every iteration, I'm gonna ask the question, is the current number bigger than the number to its right? If it is, I'm gonna swap the two numbers, but then I'm also gonna change the value of my flag to indicate, oh, it turns out it was false that it was sorted. Okay? Which means that then when I come down here to the while, I say while not 0, which is true, it goes back and does it again. Okay? Let's say we had this. One, two, four, three. Okay? So what would happen? I still compare 1 and 2. Then I compare 2 and 4. Then I compare 4 and 3. I have to swap. 1, 2, 3, 4. So at the end of that iteration of I is equal to 0, so while the do while, that was the first pass of the do while, right? I went through, I compared 1 and 2, where I compared what's in the first 2 positions, the next 2 positions, the last 2 positions. I compared all those. I found one thing out of place, so I swapped it and also set my sorted flag to 0, so I do it all again, right? Now I'm gonna come back to the top. I reset, sorted, set it to once. Okay, let's assume that it's sorted, unless I prove otherwise. Compare 1 and 2, compare 2 and 3, compare 3 and 4. The I loop stops, okay, because it just went to the end, but I never changed sorted, so now the while, or the do while breaks, and I'm done.
How come it doesn't just break out the second you go back up to sorted equals 1? Am I missing something?
Well, there's 2 loops here, right? The outer loop says keep repeating the inner loop until it's sorted. So I went through the first time, comparing the values here, and when I set sorted equals 0, it means now this test will be true. So it runs again. I'm gonna come up and reset it. Now I'm gonna assume again that it was already sorted. But this time I never changed this value, so as I come through, 1 and 2 are fine, so I don't enter the body here. 2 and 3 are fine. 3 and 4 are fine, so I never reset the flag, and the loop stopped, and now I'm done.
I mean, is there a possibility that, like, what if it was like 2, 1, 3, 4, it checks it, and then never mind, I don't know.
The point is, I'm gonna start by assuming it's sorted. If that turns out to be true, then I still have to do my 1 pass. If it turns out to be false, I need to go back through it all again, because it's only once I'm able to go through all the data and never have to swap anything that I know it must have been sorted to begin with. Right? I can't just look at data and know it's already sorted. I have to somehow do a comparison. Even as a human, you don't think you're doing that, but that's what you're doing, right? You somehow have to be looking at things to know if they're sorted or not.
How is it different from the previous one? Because in the previous one, we also said it has to go over once to make sure it's sorted or not.
Because the previous one went over every time. It did this, it said, I'm gonna pass through once where I do 3 comparisons, and I'm gonna pass through again where I do comparisons, then I'm gonna pass through where I do 1
So it
comparison.
didn't recognize that it's sorted
Right.
kind of stuff, okay.
It was hard, that's why best, worst, and average were all the same, because it says, I don't care what the data is, I'm just gonna go through every single time, right? It'd be like if you're searching an array for something. If you say, the moment you find something, quit, you might get lucky and find it the first time and you just quit, right? But if you say, well, even if you find it, go all the way to the end, well, then it always takes you in comparisons. The previous one was like that. Whereas this one says, once you're done, or once you know that it's sorted, it still takes another pass of no swaps to know that with certainty. Well, then we can stop. Okay? Now I could tweak this some. I could take this, because once again, there's really no reason to go all the way to the end I could do n minus one minus I, but this is gonna make the math easier for the average case. Okay? Okay, everyone with me? Alright, so now what's best case? Data's already in ascending order, right? I have 1, 2, 3, 4. So I compare 1 and 2, compare 2 and 3, compare 3 and 4. How many comparisons did I do? 3. And what is that in terms of n? Right. So it's big O of n. Technically, it's theta of n. Okay, so we change this to theta. Because I still have to do those n minus 1 comparisons. I have no, without knowing something about the data, I have no other way of determining that the data is already sorted without passing through it once. Okay, it's just impossible. Unless you got magic working for you or something.
Was it data of n instead of big O of n?
Well, what does theta of n mean?
The average between the upper bound and lower bound.
I would call it the average. Remember, we have this, if and only if, big O of some function is the same as big omega of the same function. Well, I just said, what's the lower bound on this? I still gotta do n minus 1 comparisons. I don't have any flexibility on that. If you give me this specific permutation, 1, 2, 3, 4, which is sorted, it takes me n minus 1 comparisons. That's both an upper and lower bound. It just takes exactly n minus 1, right? When we get to the average case in a moment, we're gonna say, well, I got lots of different permutations. What's the average of those? Now it's not the same, right? Because you're saying some of them, this is one of the possible permutations, which takes n minus 1 comparisons. But if it's in reverse order, it takes a lot more than n minus 1 comparisons. Does that make sense? Corman tends to use big theta a lot, which is arguably better because it tells you more, right? It gives you, it says you have big O of this function as well as big omega of the same function. So it's telling you two things. Right? Questions about that? What's worst case then? Exactly. Worst case is gonna be reversible. Sorry, let's put this here. Maybe in descending. Let's go through and see how this works. So I have this data, so compare 4 and 3, I have to swap. I compare 4 and 2, I have to swap. I compare 4 and 1, I have to swap. And 4 are biggest numbers in the rightmost position, okay? So this is what it looks like after the first pass. So I went through my for loop one time, and that was the result. Okay? So I had to do some swaps. It only takes one to force the loop, the do while to repeat. So I go back and start over. I compare, what do you have, 3 and 2. 3 and 2, I have to swap. I compare 3 and 1, I have to swap. I compare 3 and 4 by the way I have it implemented, but I don't swap. So 2, 1, 3, 4 is what it looks like. Alright? I had to swap, I start over. Compare 2 and 1. I have to swap. Compare 2 and 3, it's fine. 3 and 4 is fine. But I still had one swap, therefore I gotta do it all again. So now I compare 1 and 2 is fine, 2 and 3 is fine, and 3 and 4 is fine. And now I stop. Okay. So let's see what the cost on that is. This is still worst cost on the right here, or yeah, worst case equal. So this part right here, the first pass through at n minus 1 comparisons. Then the next part, at n-1 comparisons. The next part, at n-1 comparisons. At this point, it's sorted, but I don't know that yet, so I have to still do another n-1 comparisons. So this is n outer passes, or outer blue passes. So this last one simply confirms that it's sorted. Okay. So that says my upper bound. That's actually also my lower bound here. So my big data, really, we could do that. Big data here, well, let's write down what the function is first. So what's the function? I have n-1, n times.
N squared minus n.
Right, so n times n-1, so n squared minus n, so it's big data of n squared. Everybody understand that?
Is there a more mathematical or like rigid approach to determining the best or worst cases, or is it best just intuitive, basically like this?
I mean, I think most of the part is intuition. You look at it and go, okay, if you only have to do it one time, that's better than doing it n times. There's probably situations where you can't do that, but I don't know what they're off the top of my head. I mean, you could, of course, as data gets bigger, it's difficult to enumerate all possibilities, but if you do enumerate all possibilities, you'll find out what the best and worst is gonna be here, right? Questions about this? So notice on this one, our function was n squared minus n, but before, when we did the other version of the loop, of the bubble sort, we said our function of n was n squared minus n over 2, which is half what that is. Why do you think that is?
Do you do a check on this last one?
No, remember the previous one, we did predetermined number thing. Well, think about it this way. Trying to think where I got this. Need this anymore? Big check progress.
Why were we using big O in the first bubble sort example, but now we're using big data?
I just realized I could apply that.
Oh, okay.
I mean, for the other one, so, when you say the previous one, you talking about best case for this one or the previous algorithm?
The previous bubble sort we did.
Those are also all thetas as well,
Okay.
technically. I don't want to erase prematurely.
We did have some because of the condition of not minus.
Right.
So we are stopped swapping the last numbers.
Right. You're right. So what she says is correct. So in this case, let's think about how the loop's written. Because I always had, so my test was always I less than n-1. It didn't vary. So it said on the first pass, I do those n-1 comparisons. For the next pass, I do n-1. Next pass, I do n-1. Next pass, I do n-1 for worst case, right? But on the previous algorithm, it did n-1 for the first pass, it did n-2 for the second pass, n-3 for the third pass, n-4 for the fourth pass. So let's make this triangle, and eventually it only did one comparison at the end, so it's really half of these. You see that? So that's the reason why. So even though they're both n squared in worst case, the other one was actually faster. It does half as many comparisons.
In the worst case, or the best case, it's a lot
Correct.
slower.
Yeah.
Right.
Yes.
Questions about that? Let's look at average case.
Best case में faster.
And mix these two together include in the second version that we had, but add the condition of n minus I as well.
Sure. And that's what I said. It just makes it more challenging to do just what we're doing now. In fact, I was talking about this in the earlier section today, so I couldn't figure out how to do the average case for the one like that. So I looked in Canute. If you don't know who Donald Canute is, he's basically considered responsible for modern algorithmic analysis. So, he was looking at bubble sort, and he said, yeah, that was a lot of work to do his average case analysis, which is kinda like Newton telling you a calculus problem is hard, right? It was rough. But we'll be able to do it this way without a whole lot. It was still a challenge, but, this will make more sense, right? So let's figure out, so what's the average case? So for this, well, actually what he did average for comparisons. What I'm gonna do is average number of swaps. Because it's a lot more challenging to figure out how many comparisons it does. Okay, because a lot of it depends on where the numbers are at. You know, if I have this, 1, 2, 3, 4, 6, 5. Well, even though these are all sorted, I still gotta get to the end. So I had to do comparisons to work my way down before I figure out these two are the ones that are out of order. That's a lot more challenging to figure out from a probabilistic perspective where things could be and what the odds are and what the cost was, okay? It's a lot more easier to figure out, basically just count swaps. Because really it comes down to this, so how are we gonna look at this? So what we need to figure out is this. So this is gonna be total number of swaps. And that's over all permutations of the data, okay? Total number of swaps, all permutations. Divide by the number of permutations. Alright? So if we look at what we had before, when we had our best case scenario, we didn't perform any swaps, right? So it was 0. And if we look at this case, you can see I had to swap, had to swap, I had to swap, I swapped, swapped again, swapped 6 times. So in the worst case, I swapped 6 times. Okay? So it turns out, at least for these 4 numbers, it's gonna range anywhere from 0 swaps to 6 swaps. Okay? We need to figure out, for all the permutations we have, what would be all the totals of those? 0 one time, 6 another time, 5 for some other time, 4 for another time. Add all those up and say, out of all the different ways, the permutations, or how many different ways are there to arrange those numbers, average it out. Right, so the number of permutations is n factorial, right? Because there's 4 different ways to choose the first number. For each of those, there's 3 different ways to choose the second number. For each of those, there's 2 different ways to choose the third number. Finally, there's 1 way to choose the last number. So right, so in this case, we have 4 factorial, which will be 24 permutations. Okay? Now we should have to figure out how to determine swaps. Okay? So let's write down the definition. So here I wrote, when a pair of elements, which don't necessarily have to be adjacent to each other, are out of order, and that means relative to each other, that's called an inversion. And ultimately, what that means for us, that each inversion leads to a swap. So let's say I have these numbers right here, 3, 2, 4, 1. So what are the pairs that we're talking about? Well, what we're doing is taking each of these numbers and comparing it to the numbers to its right, because that's how ultimately they'll be compared for sorting, right? So here are the pairs are 3 and 2, 3 and 4, and 3 and 1. Okay, and then I'm gonna compare 2 and 4, and 2 and 1, and finally 4 and 1. Okay? So then the question is, how many of these are inversions? So if I look, 3 and 2 are out of order. So that's an inversion. 3 and 4 are fine. 3 and 1 are out of order. Okay? 2 and 4 are fine. 2 and 1 are out of order, and 4 and 1 are out of order. So we have 4 inversions for that permutation. That's one. Okay? So out of the 24 different ways the arts are arranged, those 4 numbers, that's one permutation, and that specific permutation has 4 inversions. Okay? Or go ahead and that. You basically need this part? Let's sort that, and all I'm gonna do is write down the results of swaps. So we'll start with the original. Alright, so we would compare 3 and 2, those would be swapped. 2, 3, 4, 1. I would compare 3 and 4, compare 4 and 1, those swap. Alright, so we said, trying to keep track of these. We go through it again, 2 and 3 are fine, 3 and 1 are out of order, so they would swap. Compare 3 and 4, they're fine. Compare 2 and 1 again, so it'll be fine. Then compare 2 and 1, they're out of order, get 1, 2, 3, 4. Compare those. So I swapped here. So 3 and 2 were inverted, so I swapped them. Compare 3 and 4 is fine, so I'm counting these. Compare 4 and 1, they're out of order. 2 and 3 were fine, 3 and 1 were out of order, swapped. 1 and 4 are fine. Compare, 3 and 4 here. Compare 2 and 1 again, they're out of order. Swap. So 1, 2, 3, 4, there's our 4 swaps that corresponded to those 4 inversions. Okay? So how do we use that? Well, we just need to somehow come up with a way to say for each of these permutations, how many inversions does that lead to? Which can vary, right? So let's think about this. Our inversions, our permutations. So we have 1, 2, 3, 4, and 1, 2, 4, and 3, and 1, 3, 2, and 4, dot, 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 all the way down to 4, 3, 2, 1. Okay? So we have our 24 different permutations. At the top here, this permutation is actually our best case scenario, right? Because there are no inversions. So 1 and 2 are fine, 2 and 3 are fine, 3 and 4 are fine, there's 0 inversions. Therefore, if that was the set of data I had, if that was the permutation I had, well, then I would have to swap anything. And our worst case is at the bottom. Now everything is inverted, right? 4 and 3 are an inversion, 4 and 2 are inversion, 4 and 1, so we look at it this way. So inversion, 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 that's 3. 3 and 2 are inverted, 3 and 1 are inverted, and finally 2 and 1 are inverted. Okay? So in reverse order, so it turns out in this case it was 6. But how do I get a formula for that? Well, let's look at what I did. If I have n numbers, okay, using the leftmost number, how many pairs were there? N minus one, I had 3 pairs, right? 4, 3, 4, 2, 4, 1. And then when I move over a number, this is technically true for all these. I could do it at the top. But if I say, okay, 4 and 3, 4 and 2, 4 and 1, that's the n minus one. And then move over and say, what are the pairs with 3? 3, 2, 3, 1. N minus 2. Move over to the next one, it's gonna be n minus 3. And eventually at the bottom, I'm gonna end up with only the last 2 numbers, which would be 1 pair to consider, right? I'm trying to come up with how many pairs there are. So these are pairs, the sum of these. So what's that sum? N minus 1 plus n minus 2, right down to 1. Which is really equal to 1 plus 2 plus a dot plus n minus 1. Okay, so number of pairs is equal to n minus 1 times n minus 1 plus 1 over 2, which is really n times n minus 1 over 2. Here we said n was 4. 4 times 3 is 12, divided by 2 is 6. That's how many pairs we have. Okay? Everybody see that? Everybody with me? All right. So, how do I use that? So sometimes I get 0, sometimes I get 6. Of course, worst case is 6 now, but now we have a formula for what the worst case could be. But think about the permutations we have. For every one of these permutations, there's another permutation here that's in reverse order. Okay? For every permutation, there is another permutation. Whose order is the reverse of the first, or the other.
Sorry, how'd you get the n minus 1 plus 1? It says pairs equals. How'd you get the n minus 1
Well,
plus
remember our
1?
formula was p times p plus 1 divided by 2 for the first p integers?
Mhm.
P here is n minus 1, right?
Oh, okay, yeah.
Alright. Everybody. So everybody understands what I'm saying here. So what I'm saying is, you'll see these here on the end. One of my permutations is 1, 2, 3, 4. Therefore, I also have a permutation that's in reverse order of this. 4, 3, 2, 1. One of the permutations is 1, 3, 2, 4. Okay, there's a permutation that's 4, 2, 3, 1. So what's the point of that? Well, if a pair, AB in one of these is an inversion, then we have the pair BA in the other. That isn't an inversion. So what it's saying, for any pair you choose in one of those, it has to exist in reverse order of the other one, right? If I look at this one, the top one here, where I say 1, 2, 3, 4, 1, 2 is a pair here, So 2, 1 is a pair in the other one. Only one of those can be an inversion. Okay? So how do we use that? Well, we already said the minimum number of inversions is 0, the max is 6. So ultimately, the sum of inversions for each of these permutations and its reverse adds up to the 6. Like what we have here. This is 0 inversions, this was 6 inversions. If I look at this, 1, 2, 4, 3, let me put it here. Right, so we said 1, 2, 4, 3. The only thing that's out of order is the 4, 3, right? So it has 1 inversion. It's reverse order. Inversion would be 3, 4, 2, 1. So our pairs are 3 and 4, 3 and 2, 3 and 1, 4 and 2, 4 and 1, and finally 2 and 1. How many of those are inversions? 3 and 4 is fine, 3 and 2 is inversion, 3 and 1 is inversion, 4 and 2 is inversion, 4 and 1 is inversion, and 2 and 1 is inversion. 1, 2, 3, 4, 5, 6. What was the one that wasn't an inversion? 4, 3. Or, yeah, I mean, that was an inversion here, 4, 3, so over here it appears as 3, 4, it's not an inversion. Okay? So that means out of the 24 permutations, we really have 12 pairs of permutations, right, that are reverse orders of each other. And together, they account for 6 inversions. Everybody see that? So the top part of this, total number of swaps for all permutations then becomes n factorial divided by 2 times the number of pairs, which we said was n times n minus 1 divided by 2. That's the total number of inversions, which corresponds to the total number of swaps. And I actually wrote a program to generate all 24 permutations and checked it. I won't make you do that on the test. But it's not the whole thing. Not for 24, let's put it that way.
So that's a denominator that it gets divided by.
That's the numerator. Okay? So this is the numerator. This is saying how many swaps are there total across all the permutations. I'm saying it's all tied to how many pairs there are and how many inversions there have to be there for the number of permutations.
Is there a simplified version of that equation?
This right here? If you multiply the n times n minus 1 and the 2's, I don't know how you simplify that. Is there some other closed form solution? Maybe, but I don't know what it is.
Wait, how do we get n factorial over 2?
Alright, so I said, we had 24 permutations, right? That's n factorial.
Yes.
But we said that each of those is basically a reverse version of one of the other permutations, right? So I really have these 12 pairs, n factorial divided by 2 pairs. Together, they share the 6 inversions. This was the 6, n times n minus 1 divided by 2. This is how many pairs? Okay. So that's the numerator of that formula over here. Okay. So let's finish it. So we want an average. That would be the total, which for this problem adds up to 72 inversions. If you work that out. Okay, it's gonna be 72, right? But we said we want the average across the 24 permutations. So our formula becomes, in the numerator, we have that, n factorial over 2 times n times n minus 1 over 2, and the denominator is n factorial, which simplifies to n times n minus 1 over 4, which is n squared minus n over 4. Swaps. Questions about that? Questions about what I just did?
So ultimately, it's just the average number of swaps?
This is the average number of swaps across those 24 permutations. Comparisons was beyond my skill level. Like I said, Knuthi, you said it was challenging. Well, he said, yeah, it was some work, basically. What he said. All right. So what numbers does that work out to be here? What's the average? Well, we found out the n factorial canceled out, so we're left with the n. So what's the average number of swaps across this? Because we said the best case scenario was 0, the worst case it was 6, but we don't know what the distribution is in the middle. Okay, because some of them have 2, some have 4, some have 1, some have 5s. But the formula says n squared minus n over 4. Our n was 4. So that's 4 squared minus 4 over 4. 16 minus 4 over 4, which is 3, which is actually the average of 0 to 6. So if I had to figure out in the average case how many swaps was that particular bubble sort, the one I implemented, how many swaps does it perform on average? Since I don't know which permutation I'm dealing with, it works out to be 3. Okay? And I shouldn't mention one thing here. We always need to have assumptions. Assumption. So assume all permutations equally likely. I don't know otherwise, right? I might have a situation where I have some data that's sorted, and I basically keep it sorted most of the time, and occasionally it gets out of sorted because I have to add or subtract something. In that case, it would skew this, right? Because if it's already basically sorted, if we go, this makes more sense when we're talking about searches. But think about it, if we already basically got it close to the best case scenario, well, obviously the average comes down, right? If I said, how much effort does it take to sort this? I know it's probably pretty close to already sorted. For this algorithm, since it can stop once it determines that it's already sorted, then the average will be closer to the n-1 comparisons to start with.
So the big O of the average is also n squared, right?
Huh?
Big O of the average is also n squared.
Yeah, so for this, it's, yeah, I mean, I would still be okay with big theta on this. Let's talk about that. Any more questions about how I got there, though? Right. So something I said last week, let's talk about it again. This is not true. So best does not equal big O, and worst does not equal big omega. Okay? When you have something set in stone, so if you say it's always, I have a loop, right? I have a loop that runs for I equals 0, I less than n, I plus plus, and say print I, just write print I. If I say, okay, what's an upper bound on how many times that I gets printed, right? Well, it's n, right? Well, what's the lower bound? It's also n. But if I were to ask you, let's talk about here, if I just said, okay, I'm going to apply the bubble sort we're talking about here, the one where it can stop once it determines that the data is sorted. If I say, I don't know anything about the data in terms of how well it's sorted. Now if I say, how long will it take to sort? I say put an upper bound on it. The upper bound is going to be n squared, right? But lower bound was the n. Because it could be it's already sorted and it just passes through once and stops. Now I'm not set in stone. I have some variability there, so it can swing between the upper end and the lower end. Okay? But if I say the loop just has to run n times, That's both an upper and lower bound, it's just n, okay? Now, it's true, lots of times they get buried, because somebody may say, okay, tell me about the worst it can possibly be. Well, then in that case, I would interpret that to mean, what's the upper bound on the worst case? And if you say, okay, what's the best we can end up with? I would think that's a lower bound on the best case, right? If you're saying, okay, give me a range of how much time it's gonna take. Well, okay, lower end, it still has to take at least this much time. Worst case, it won't take any more than that kind. So sometimes they do get used together, so often people will use best and big O together and worst with big omega together. That depends on the situation. Best can have a big O and a big omega, and worst can have a big O and a big omega. Those are just bounds above and below it, that's all it means. Does that make sense? All right. Make some comments about bubble sort.
What do you mean by it's stable?
I'm gonna explain all this as soon as everybody catches up, you're right. First thing, bubble sort's performance is generally considered poor even when compared to other big O n squared algorithms. In some sense, we say everything that's big O n squared is equivalent, but in other sense they're not. When we get down into the actual functions, the cost, the underlying cost to do certain things can differ, right? That's why even sometimes you'll see that somebody may choose to use an n squared algorithm instead of a n log n if n is small, because the n log n may have a lot more overhead cost that for large n, averages out, it doesn't really cost you much. But if it takes a lot to get you going, and n is small, it may not be working versus n squared, okay? So even among those that you say are equivalent because they're n squareds, there are other algorithms that in general still have smaller underlying functions. It'd be like if you said one of them was, well, it's like the ones we looked at. We saw two bubble sorts. One of them was n squared minus n, and the other was n squared minus n divided by 2. Well, the first one then, if the data was in worst case, is smaller, right? It's half as much, even though they're both classified as n squared. So I teach it because one, it's the only one I know off the top of my head, and two, it's not that difficult to write out and understand how it works, I think. So it's a good teaching tool, but doesn't mean performance-wise it should be high on your list, right? Stability. Not all algorithms for sorting are stable. So let's say I want to sort. So sort by last name, then subsort by first name. All right, so my data is, I have Wilson, comma Tom, and then I have Smith, comma Adam, and then I have Donaldson, comma Ralph, Smith, comma Roger. Okay? So when I say sort by last name, that means Donaldson should be at the top, the two Smiths should be in the middle, and Wilson should be at the bottom, right? But then it says subsort by first name, so that means the two Smiths should be in order from Adam to Roger. Now, the way some people would choose to do that is they would sort this first by first name. There's a way to do it, which would give us Smith, Adam, Ralph, Donaldson, Roger, so Adam, Ralph, Roger, Tom. Okay. If I'm using a stable sort, notice that Adam Smith is above Roger Smith, which is what ultimately I want to have anyway. So now if I sort this by last name, it will maintain that order. If it's not a stable sort, in its process of sorting this out and putting the two Smiths together, it may scramble the Adam and the Roger. Does that make sense? So for things that are considered equal, if I'm sorting by last name, the two Smiths are equal. If something's considered equal, a stable sort won't rearrange them. It leaves them in the order they were already in. Okay, and there's times you want that. You don't want sorting in one way, like if you use this scenario. You don't want to undo something else you did. Now, me personally, when I sort, I don't do that. I just go through one time, or however many times the algorithm really does, but I ask all my questions at once. I just say, which is the way I would do it if I was doing it by hand. I'm gonna go through doing my last name, and then if I see they're the same, well, then I go ahead and check the first names and fix that if I need to. That's how I prefer it. Right? Sorts in place. So, what was the temporary storage that we had to use? Well, it was just int temp, right? So I had my array, and so we would say here the space complexity well, actually, technically, these are two different things. Sorts in place means I'm rearranging stuff within the array, all right? But the space complexity for this would be big O1. Whatever the cost of the object is, I store one of those at a time, right? Whereas some sorting algorithms will basically make copies of the array or subparts of the array, save those, and then rearrange things, which means you have to have additional space. So if I got a billion things in the array, I don't necessarily wanna make another copy of that, just to move things around, right? So you may have a situation in which you care whether or not it uses the space you've already allocated, or it has to have a bunch of additional space. Okay? And then finally, for the last thing, notice I underlined the might, because this is largely based upon my opinion. Some people say, oh, you never use bubble sort. It's the worst thing out there, your children will die or something. Just don't use it. There's always something better. But that's not necessarily true. These are the situations where I might think it's okay, and actually probably a combination of these. N is small. If N is small, if you say, well, if I use bubble sorts, it'll take a second to sort this. But if I put 2 days of work into implementing quick sort, I can do it in a quarter of a second. Well, I can implement bubble sort a lot faster, right? So what's the difference between a second and a quarter of a second? If you're doing it once or twice, it doesn't make any difference. Now, if you're doing it a billion times, that starts to add up. Okay? So it's a judgment call there. What if the data is already nearly sorted? We already saw if you use the version that can detect when the data is sorted and stopped. If it's already nearly sorted, it doesn't really have to make that many passes. Whereas some sorting algorithms make no effort to look and see if it's already sorted. They just do what they do. They may always do what they do fast, but they do the same number of steps. They just go through and move all the stuff and they go and put it back together. That's just the way they work. So on average, they may be much better, but the data's already sorted. They have no way of detecting it and stopping, okay? And the last thing, one of the nice things about bubble sort is we know after K passes across all the data, the K largest values will be at the end, right? Whereas some sorting algorithms don't do anything like that. They do what they do, and then the only thing you can guarantee is that by the end, everything will be sorted. But along the way, I'm not necessarily guaranteed that I'll be able to find the top K elements of the array. So I think every algorithm that's valid has its place, right? You learn the pros and cons, and then you make a judgment call for your situation. Okay? Questions about that? All right. So let's look at another one. This would be insertion sort, which some people think you should use instead of bubble sort. And this is actually out of the book, so you can use it. The problem is Corman though jumps right into it, and like chapter 2, your head explodes trying to figure out what's going on. So this is from Corman, page 18. And this is pseudocode. start talking about pseudocode. Originally, I'd rewritten this in C, but I decided to go back to the pseudocode. And the reason why is because you have to get used to looking at pseudocode and making adjustments. In particular, how are the indices indexed, okay? What's the index of the first element in this case?
Two.
It's 1. J starts at 2, so it's gonna start on the element to the right of the first element. But you can't count on pseudocode using your programming language's indices, okay? So this one says for an array that has n elements, they're indexed 1 to n. And you just have to adjust to it and figure out where to adjust, okay? That may or may not be difficult, but another thing to keep in mind is sometimes, in particular, if you're trying to do things that involve mathematical formulas, the mathematical formulas may be written specifically because that's the way the math works. So if you say this is a summation of I equals 0 to n of, say, x to the I power, well, if that's what the math says it has to be, it has to start at 0. That's just the way it is, okay? So if you said, well, maybe I want to take these values, so let's say it's really this, let's say it starts at 1, right? And you say, well, I have some reason for wanting to store each of those n values, right, 1 to n, so there's n. If I want to store each of those and I'm writing a C program, what do? Well, in terms of producing this, these need to go from 1 to n. But then you gotta make the adjustment to say, okay, for my array where I'm storing them, I go 0 to n minus 1. So you pick one and fix the other one. That's the way it is typically, okay? And you think that wouldn't matter, but I've had people like in my signal processing class where I give them a formula that's like this, and they use a language that has different range of indices. And I had people 2 weeks in a row doing it wrong. Even after pointing out the first week, quit doing that, and the next week for the same code, they did it again. So you just have to make that adjustment. Okay? So let's look at how insertion sort works. All right, so start with their index at 2 because it's going to process these subarrays. So the way it works is it assumes the leftmost element is a subarray. Okay? Which of course, since it only has one number, it's already sorted. So then what it does is it's going, in this case it'd be the key, will be the 3. The key equals a sub j, which starts at 2. Let me remove this, because I'll rewrite the array. Yeah, well, let's do this. So here's what the array looks like. Right? So the key equals 3. So what it has to do is it moves to the left, comparing the key to the elements to the left, until either it runs out of space, right? So since our indexes start at 1, that means as long as the index is above 0, we haven't went too far in the array, right? If this was in C, I'd make this minus 1, right? Or until we find a spot where the next number is smaller than the key. So what we're doing is we're moving slowly to the left, trying to figure out where do I insert this number, okay? But remember, one of the problems with arrays was we don't really insert in the sense of we separate values and slide something in there, right? It's not like a linked list. So what it does on each iteration is it basically copies over the value to the right. So it's going to look at 17, it enters the loop because I is greater than 0 and 17 is bigger than 3. So it overwrites the 3 with the 17. Then it gets up here, now I, because it decreased, now breaks the test. We went as far to the left as we can. And it says stop and put the key where it needs to be. So it writes 3 in place of 17. All right? So now here's our subarray, 3 and 17. So now we want to insert 61. But immediately we find 61 is the key. And the key is bigger than 17, therefore you leave 16 where it's at. Although technically the way the code's written, it says, okay, overwrite 61 with 61, right? So just write 61 here again. So now there's our subarray, 3, 17, 61, which is sorted. So that's why I have this part here. We're inserting a sub j into a 1 dot 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 j minus 1, which is always going to be sorted. By the time we finish on each iteration of the loop, the subarray will be sorted. We just have to find out where to put the new element. So we compare 0. So now, the key is 0. Compare 0 to 61. 0 smaller, so it's gonna write 61 in that position. Then it's gonna compare 0, and technically we still have 61. So at this point, we have 17, 3, 61, 61, right? Because we stored temporarily the 0 as the key. That's our temp, okay? So now we'll compare 0 to 17. It's smaller than 17, so I'll overwrite the first 61 with 17. Then I'll compare 0 to 3. 3 is bigger, so I'll override this first 17 with 3. So at this point, the array is 3, 3, 17, 61. We're finally at the end where I cause the loop to fail because I ran out of places to put things. And I override the key in the last position, and now it's sorted. That make sense?
Cool.
Alright. So let's analyze that. Any questions? Let's do that. Best case. Data's already sorted. Okay. So how many times does the loop work? Well, for each of the n minus 1 times, it still has to come down here and ask the question, is I greater than 0 and is the left value greater than the key? And the answer is always going to be no, the left value is not greater than the key. So what are we evaluating? What's for this best case for comparisons? That's typically what people would count. I only switched to swamps on that last one because I couldn't do the math for the number of comparisons. That was the one I was talking about, right? Data is already sorted. So, for each of the n minus 1 values that j takes on, we have to ask this question. Therefore, I still have to do n minus 1 comparisons, right? The best case. Right? So this n minus 1 comparisons. So we could say this is big theta of n, or big O if you want. Right? Questions on that? Question about that before we look at worst case. What is it? Yeah, worst case. Yeah, go right here. Here, the worst case is the data is in descending order. It's completely reversed. So what happens here? So let's write some numbers out and see how this works. We'll do it right here. Right? So we start off 4 is our subarray. Okay? So then we compare 4 and 3. We enter inside the while loop. We override the 3. We come up, we test again. Okay? This time it fails, right? Because we're already at the end of the loop. So it took 2 comparisons. Right? One to compare to 4, and then another one to make the test fail, if that's what we're counting. All right, everybody with me on that? Now 2, I compare 2 to 3, compare 2 to 4, finally compare a value that I won't be greater than 0 anymore. It really took 3 comparisons. Right? So this took 3 comparisons. Then we get to the 1. Compare to 2, compare to 3, compare to 4, one more to break the test. It was 4 comparisons. Okay? So, what was the cost on that? Well, this was 2 plus 3 plus 4. But n was 4, so this is really 2 plus 3, 2 plus 3, plus dot dot dot, plus n. And what is that?
No, it just.
No.
Well, what's it similar to what we've already seen? So we know 1 plus 2 plus dot 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 plus p is equal to p times p plus 1 divided by 2. So how do we use this here? Subtract 1, right? The difference between these, if I sum up the integers from 1 to 4, there's gonna be 1 too many here. Right? So this right here has to be n times n plus 1 divided by 2 minus 1. Everybody see that? Which works out to n squared plus n over 2 minus 1, and ultimately, let's stay at n squared. So far we had best case was n, worst case is n squared. Okay, now we have to do average case. That's where the challenge comes in. Everybody understand this stuff? How it works? I was thinking earlier, when I did this in the earlier section, I'd actually done them either, I can't remember now if I was doing comparisons or if I just wasn't paying attention, but I had done it 1 to n minus 1, but it still works out to n squared. All it does is shift it by 1. Well, you add in 1, you subtract out n, because you only go to n minus 1, but it still works out. So now let's look at the average case. Any questions on what we've done so far though? So let's write out some stuff. Anybody still need the part on the right board? So I'll write this out so you know the steps on it. So this goes back to what I said earlier. For each iteration of the loop, there's gonna be k values to the left of the key, right? Start with 1, then we have 2, then we have 3, and so forth. But each of those requires potentially k+1 evaluations of the while. It depends on what the date is, right? I might get lucky and it's already ordered and I have to test it once, or it might be in reverse order and I have to go past it and essentially insert my value at the very beginning of the loop, right? Which only stops, the while loop stops because I is not greater than 0 anymore. Okay, so it's always k plus, so it ranges from one comparison to k+1. Okay, so let's create a table. And I encourage you to do the same when you're doing these types of things. So what we need to do is ultimately, in order to find the average value, we're gonna find the average of the averages, all right? We don't know which permutation we're gonna get. So we have to figure out for each one, what was the average things. So when k was 1, okay, it could be that the key is bigger than the value to the left, so it took one comparison. Or it could be smaller than that, so it really took 2 comparisons, right? Because we had to go all the way to the left. So it was 1 plus 2 divided by 2 is 3/2, which is 1.5. Right? When k is 2, then we can have 1 or 2 or 3 comparisons, right? Because we have one extra number. Divide that by 3, that's gonna be 6 divided by 3. Which is 2. 3. So it's 1 plus 2 plus 3 plus 4 divided by 4 will be 10 divided by 4, which is 2.5. Right? And we eventually work down to where there's n-1 numbers to the left in the subarray. So we're inserting the nth value somewhere in the n-1 positions. That'd be 1 plus 2 plus dot dot plus n divided by n. Okay? Now somehow we need to add all these together. The problem is, that's somewhat challenging, right? Especially at scale. So I really want to come up with a closed form solution that allows me to do it, right? This says, I don't care how big it gets. You just plug k in there and it's gonna tell you what the number is, right? That's what my closed form solution is gonna be. So let's see if we can spot a pattern. We're getting the n factorial.
I mean, it's factorial. Oh, no, not factorial, never mind, never mind.
Let's look at what we have here. So where did the, k was 1, what was the last value here? 2, which is k plus 1. And we divided by that. When it was 2, we went to 2 plus 1, divided by 2 plus 1. All the way down, n-1, you add 1 to that, that gives me n. Okay, so what my pattern was this. 1 plus 2 plus k plus 1 divided by k plus 1. Alright, so I'll pull out the denominator, but the top part is the sum of the integers, this is really k, look at it that way. 1 plus 2 all the way up to k plus 1, right? Which once again is the sum of the first k plus 1 integers. That formula's never going away, right? That simplifies to k plus 2 divided by 2. next time when we have some time, we won't have time today, but next time, we're gonna prove it with induction, alright? But for me, even when I'm gonna prove something with induction, I like to spot check. I already claim I have some numbers, right? I already claim when K is 1, I get 1.5. I claim when K is 2, I get 2. When K is 3, I get 2.5. If that formula is really correct, I ought to be able to reproduce those, right? Now, I will tell you, for me personally, when I make arithmetic mistakes or I get the wrong pattern, for some reason, it turns out I still can produce a pattern that works for the first couple of numbers, okay? Which is why you can't say, well, I tried 2 numbers, so it must work for every number. That's not proof, okay? Because there's too many times it can still sort of work out. But it usually is a good way to determine something's wrong, right? As a counterexample. If I use that formula and plug it in for 1 and I get 23, I know something's wrong somewhere. Okay, so let's try. K plus 2 divided by 2. So I'm thinking, so my close form averages says, okay, K is 1, and 1 plus 2 divided by 2 is 3 halves. 2 plus 2 divided by 2 is 4 halves, which is 2. 3 plus 2 divided by 2 is 5 halves, which is 2.5. So it does look like it's working, and we'll prove it with induction next time. Okay? So what does that do for me? Well, now I have a way, K plus 2, where I can say, this is K plus 2, this is K plus 2 for a different K, this is K plus 2 for a different K, and so forth. I have a much easier way to produce the sum of these averages, right? Because each of these is an average. 1.5 is the average for this one of the possibilities. 2 is the average for these. 2.5 is the average for these. But if I try to leave them in this form where it keeps scaling and getting bigger and bigger each time, I don't have an easy way of trying to add those up, right? So, summation. K equals 1 to n minus 1 for the formula. K plus 2 over 2 is, I just plug these in, I get 3 halves, plus 4 halves, plus 5 halves, sorry, halves, plus dot dot dot, plus n minus 1.
Minus 1. No, n plus 1.
Oh, yeah, n minus 1 here, plus 2, so plus 1, this is
Yeah,
plus
yeah,
1.
yeah.
Sorry, maybe something's off. All right?
Right.
Is for n greater than or equal to 2, all right? That sum then becomes, what do I have here? Every one of these is divided by 2. So I'm gonna pull out the 1/2, which gives me 3 plus 4 plus 5 plus dot dot plus n plus 1. What is that? The sum of the first n plus 1 integers minus the 1 and minus the 2. Okay, you gotta get comfortable with taking the formula you have a closed form for and somehow squeeze it into your situation. So it becomes 1/2 of these. So this is gonna be this, or n. So this would be n plus 1 times n plus 1 plus 1. How about 2? Minus 1, minus 2, is really minus 3. And this simplifies to this, you can work all it out. I make it 1/2 of n squared plus 3n plus 2 over 2 minus 3. That's what that will become if you simplify that. Which you should do. Right? So, if I factor through, so I can multiply it through by 1/2, so this becomes a 4 here, this becomes 3 halves. All right? Let's put it right here. So this becomes, it's gonna be n squared divided by 4, plus 3n divided by 4, plus 2 divided by 4, minus 3 halves. Now I'm gonna write it a certain way just to start exposing you to it. I already know where this is gonna go, right?
Yeah.
N squared is where most of it's gonna come from, right? As n gets bigger, that's gonna carry the size, right? So one of the ways you'll see people write this at times, they say, well, I want to focus on this part, but not necessarily lose the other part. Well, I can put a bounds on this other part. What's the big O of the last part?
And
N, right? So big O would do theta. So we could say this is n squared divided by 4 plus big O of n for that part. But overall, the average performance, or excuse me, the average of the comparisons, we would say is big O of n squared. Does that make sense? So people were asking me earlier about averages. Is that starting to make sense now why we're doing that? We don't know how things are gonna work out, right? And of course, you still have to have some underlying assumption. I'm making assumptions about the probabilities here. Everything is equally likely. If I know that's not true, I can try to incorporate it, but obviously it's a much more challenging problem to say, oh, well, this particular permutation may show up 12% of the time or something, and that's will make it real rough to do. Any questions though?
मैले बुझेन कसरी निकाल्नु एक वन भन्नाले एन प्लस वन एन प्लस वन
No, I'm saying
यो पनि निकालेर
this right here is the number
त्यो
of
माथि
given
त्यो माथि
probability.
यसलाई सिम्प्लिफाई गरेर अब यसले यो सबै जोडा त होइन यो भनेको चाहिँ अहिले के को टर्ममा हो के को टर्ममा हो अनि यसलाई प्लस वन एन माइनस वन भनेर त खास के यो के प्लस टू के प्लस टू के प्लस के प्लस वन हो ए त्यो टू लेख्यो नि त हामी होइन टूदेखि सुरु भयो भएर यसले वान हटाउनु पर्ने नि होइन के को भ्यालु भने एउटा ऱ्यान्डम भ्यालुले आफू बनाइदिएको भ्यालु हो अब त्यो त त्यही त्यो एन माइनस वानवाला फर्मुला लाग्यो कि एन प्लस वन डिभाइडेड बाई टू छ नि त्यही त फर्मुला छ नि फर्म हेर न यसको वन प्लस टू प्लस वन प्लस टू प्लस थ्री प्लस डट डट एन गऱ्यो भने यसको समेसन भने यो होइन त अब त्यसको सट्टा एनको सट्टा के प्लस वान छ होइन त्यो भनेको के प्लस वान र के एन प्लस वन बाई टू गरेको यहाँ चाहिँ अगाडि वन बाई थ्री त्यो तल के प्लस वान छ त्यो बाहिर त्यति हो